advocate what's called the thick database paradigm. So use PL SQL in the database, use the database features instead of using it not and acting as if it's a bit bucket. So you can imagine that I'm a bit frustrated by the average application that I see nowadays, which does not use the database in an intelligent manner at all. Data modeling seems to be old school. I was raised in an era where we learned how to model data, how to create database designs. Apparently, a lot of people have moved on, whatever that is. I think data modeling is still the #1 critical success factor of any database application. Object-oriented design was taking over the world. I nowadays, however, also see that it seems to be on the downhill. And PL SQL is proprietary. Please don't use it. Everybody calls that. Everybody says that. So the database is a bit bucket. Especially don't put logic, business logic in there, because it won't scale. And with that, I strongly disagree, and I hope you will all agree with me after 50 minutes. So what if someone told you that moving business logic out of the database actually puts more stress on the database? Or the other way around, moving business logic into the database makes the database more happy because it has less to do. That's counterintuitive, right? But that's what I'm stating here. So basically I'm telling you that you can save on these expensive database CPU licenses, and by the way lots of application server hardware also, by adopting what we call the thick database paradigm. I tweet. I usually use the hashtag ThickDB when I tweet about thick databases. So do I have your attention now? I will set up a storyline in a bit of an unconventional manner, because I'm sure for those who are interested in this topic, they might have heard other people talk about this and maybe come to the same conclusion. But I'm going to use a different route than I usually do to come up with the conclusion that moving business logic into your database enables you to buy smaller database server hardware. So I will introduce some terminology, explain a bit about technical architectures, and then I'm going to do a report on some measuring that we have done with a program which was built outside the database and which was built inside the database, and we started running it and we started measuring and comparing it. First, I've used the term now a couple of times. What is business logic? And what do we mean by no PL SQL and thick DB? I just want to make sure we are all on the same page here. Our context is, of course, data-intensive database applications. There's always a data store with a bunch of relational tables. And on top of that, we have a lot of logic that queries or writes, insert, updates, deletes the data in the tables. Potentially lots of reports, batches, many users that are using such a system. Yeah, so that's the context. And you may have a different context, but the majority of the business applications are within this context. So these business applications conceptually can be dissected into 3 tiers. The interface tier, they can be human or software interfaces to other systems. The data store at the bottom, and then everything in the middle, which I now label as business logic. If you go to Wiki, there's actually a pretty good definition on what's business logic on Wiki. Business logic determines how data can be created, stored, and changed. It is contrasted with the remainder, being the bottom part, managing the database, and the upper part, displaying the user interface. Yeah? So here too, it's the stuff in the middle. So it's the code that has the data access calls in it. And since we live in a relational SQL world, it's the code into which you embed all the SQL statements that then get executed at the database tier, right? So I can make it a little bit more abstract. Business logic is the code that composes these queries. They may be hard-coded, they may be created dynamically, and then executes them or composes the transactional statements in circuit based deletes. And often, of course, it's a mix in between these two. Now, so that's business logic. Now, what's the no PL/SQL approach? The no PL/SQL approach is where PL/SQL is not the language where the SQL statements that access the data are embedded in. Yeah? So there are many no PL/SQL approaches. SQL can be embedded in .NET software, in C# software, in Java software, you name it. Some other language that lives outside the database. By the way, I mentioned Java, of course, because that's the most often used programming environment to build these kinds of applications, the context in which we live. Object-oriented designs are used, objects are mapped to tables, often via an ORM tool, and the developers, they don't see these SQL statements anymore. So there are no PL/SQL approaches, typically in Java, the Java world would be that, where the developer is totally unaware of the SQL that's being generated towards the database. These architectures often result in what's called chatty applications. Chatty in the sense that they chat a lot with the database. There's a lot of SQL going back and forth between the code that lives outside the database and has the SQL statements and the database that accepts the SQL statements and executes them. Row-by-row processing, single row processing, also called slow-by-slow processing, is the rule in these architectures. Whenever I see a no PL/SQL Java application, this is how they how they interact with the database. Now, on the other hand, in the thick database approach, PL/SQL is the language that has the embedded SQL statements. Yeah? So it all takes place in the database, ergo the adjective thick. And we expose the business logic APIs for the user interface via package procedures or functions, maybe views with table functions or not. You have lots of possibilities to expose to the interface layer. Yeah, so those are the three terms that I just wanted to make sure we all understand. Business logic, code that executes SQL to query and manipulate data the way the business required is to be done. In the no PL/SQL approach, it's not PL/SQL that has these SQL statements. In the thick database approach, it is PL/SQL. And by the way, in the PL/SQL approach, all options are open. You can do row-by-row processing in PL/SQL, sure. But you can do array-based processing, where you process arrays of rows at a time, or you can go set-based, which is very natural once you're in PL/SQL to write set-based SQL statements. The SQL statements are often, typically, totally not hidden for the developers. If you're a PL/SQL developer, you love and you write SQL statements. Now, I want to get you start thinking about this here. So I mentioned that in the business logic layer you have let's call it procedural code executing, and at some points a SQL statement needs to be submitted and it returns back and it continues in the procedural code. Now, in your application, do you have any idea how the percentage division is between executing SQL statements and executing the surrounding code which embed these SQL statements? Is your application, for instance, processing 80% of the time SQL statements and only 20% of the time the surrounding code? Or maybe the other time, do you have really complex business logic and 80% is spent in this programming language and only 20% is spent in the database servicing the SQL statements that get submitted? Any idea where your application is? You should be aware of this, I think. And I'll come back to this picture at the end of my presentation. So, I mentioned at the beginning that we did some testing actually for another presentation that we had yesterday to figure out some of the performance characteristics between these two approaches. And for those of you who attended my session yesterday, I'm going to repeat a little bit. So what we did is we have a NoPL/SQL row-by-row batch process, and we used straight Java. So we have a Java programmer that used straight Java on top of JDBC to build this batch process. Then we rebuilt it in PL/SQL, also row-by-row processing. Yes, Bring.
When you did the NoPL/SQL build, could you say that you were following some of the supposed best practice in that space?
So the question is, when we built it in Java, were we following best practices in that space? I guess not, because best practices in that space would be to use a humongous layered software architecture with a persistence framework, a model framework, a business entity framework, etc. We did not do that. We specifically targeted first, let's do it as thin as possible in Java. Yeah, so we have a very thin Java program that does exactly that, what this batch process needs to do, and submit the SQL statements, programming, prepared statements in JDBC directly. Yeah, so the programmer is actually writing the SQL statements, the row-by-row SQL statements.
But just to paraphrase that, you gave the Java unfair head start by informing your approach to intellect.
Your statement is we gave the Java approach an unfair head start by doing so.
Yes, you gave it a good turn.
Make Java look better.
Yeah.
Just so we know where we stand in the comparison.
So we have these two programs, and we're going to run them and observe the performance metrics of this little batch process. And this batch process, just 2 minutes on what this actually do. It has to do with VAT, tax clearing, where companies, they sell products to each other, and buy and sell records need to be matched to ensure that only one company claims the tax. And there's 5 tables involved on a daily basis, and this will be the run. The run will load 2 files into staging tables, and then the matching will start, where using some business logic, rows from the one table, from the sell table and the buy table are matched or not, and once they are matched, they are moved to a match table. They are then removed from the staging tables, and if at any point during this processing we hit a duplicate key on index, there's a couple of business keys on these tables, we will part the rows into some side tables. And the point is, this program does a bit of everything. There are lots of single row inserts going on into 5 tables. There's lots of single row lookups going on for deduplicating and for the matching process. There's some single row deletes going on in those 2 staging tables. And of course we have indexes on these tables, and there's some index maintenance going on. And then there's some rather simple business logic, some if-then-else logic that determines which SQLs need to be submitted inside the loop that's all processing this. And during this batch we'll generate about 5 million single row SQL statements. So let's look at the 2 constellations. On the left we have the NoPL/SQL constellation. So we're running inside a Java virtual machine which has the business logic and the embedded SQL statements. On the right, we're just inside the stored procedure, a packaged stored procedure inside the database. Again, the exact same business logic. Both, we're going to run them both single-threaded. So I'm going to run one thread in Java that does all the processing required, and one call to a stored procedure that does single-threaded all the work. And how we are going to monitor it, we're going to keep it really simple here, is we're just going to look at the CPU usage of these 2 processes. There is of course a dedicated server process involved. Once we log into the database, we're going to monitor its CPU usage. And there's the client-server process, the JVM, involved in the NoPL/SQL constellation. Obviously, we don't have a client-side in the thick database constellation. So we're going to monitor the CPU use. So I'm going to draw two charts. On the horizontal axis we'll have the time. On the vertical axis we're going to look how much of one single core is this process using. So between 0 and 100%. And by the way, we're running the JVM on the same machine as the database, so as to not be bothered by any networking phenomena that might also happen. We're just doing inter-process communication between the JVM and a dedicated server process. So here's the first baseline run. We ran this job first in the NoPL SQL constellation. It took 26 minutes to execute those 5 million SQL statements and the business logic. We saw that the JVM on average was busy 25%, and that our dedicated server that was servicing the SQL statements was busy on average 45%. Does anybody have a question about this slide? Does anybody have a question mark popping up now if you see this? Where's the rest of the time? Yeah. So the 25 and the 45, they do not nearly add up to 100%. So there's what, 30%? Some 30% gone. I'll come back to that in a minute. So here's the PL SQL run. It took 6 minutes and 23, so 6.5 minutes. And it kept one core really busy. Now, the big question is, was there more time spent in the database in the NoPL SQL run than this thick database run? So is the surface area of the 45% busy times 26 minutes smaller or bigger than the surface area of 97% CPU usage in the database times 6.5 minutes? Well, visually you immediately see it, of course. It's almost twice as much. So what happened here? I had a Java program. I rebuilt it in PL SQL with the exact same logic, and it uses twice less database CPU. Well, let's go back to the question that we had. Where's those 30%? Let's look at the AWRs, because maybe we need to change a little bit. What I did not tell you yet, but I'm telling you this now, is we were committing on every row in both constellations. If you commit from outside the database, you're always hit with a log file sync write. If you commit from within PL SQL, there's an optimization where the log file sync write is not hit. So it's actually, it may not be a fair comparison right now. Let's do a new baseline run and change the logic a little bit, just for the sake of the argument that we want to make in this presentation. We're going to commit every 128 rows. That should get rid of the log file sync wait event in the NoPL SQL constellation. So we're going to rerun. We changed the Java program, we changed the stored procedure. And we now see that Java, it executes a lot faster. From 26 down to 11 minutes. And luckily, the client side and the server side times now they nicely add up to almost 100%. Yeah. So I have 33% on the client, 66% CPU busy in my dedicated server. So the NoPL SQL constellation gained a lot. This may now be a more fair run. Let's look at the PL SQL run. Wow, it also gained a lot. Seems like just committing in PL SQL is still very expensive. Although you're not being hit by the log file sync rate, it went down from 6 minutes 23 to 3.5 minutes. But now we have two fairly comparable runs. And again, we're going to ask the question, which surface area is bigger? There still remains the 2x difference. Yeah, so we now have a fair comparison. We are using only 204 DBU CPU seconds in the database to execute those 5 million SQL statements and a bit of business logic. and we're using 437 CPU seconds to only execute the SQL, because the business logic is executed in the Java tier. This was quite a shock for me when I found this out. So what I did is, why is there such a big change? And I'm going to explain to you why there is such a big change. Just to make sure we're still running a fair comparison here, the top 10 foreground events are now, they look sort of the same. So to me this is a fair run. Both are CPU bound. Of course there's still a little bit of log file sync weight in the NoPL-SQL constellation, but I'm going to ignore that. And they both actually do run the exact same inserts, deletes, and queries and joins the same number of times. Just so to convince you that I'm not cheating here, those are the 5 million SQL statements that are running, but in both situations. So the first thing that we did is, wait, is there something, might there be a problem or an issue with Java and the way it submits SQL statements to the database? So we decided to also re-implement this little batch process in as a C program, using straight OCI, Oracle Call interface, to submit the statements. So we have a second NoPL-SQL constellation, straight C with embedded SQL using OCI. Let's run that too and see how it performs in comparison to the Java situation. It runs a little bit faster. It keeps the database a little bit more busy, 20% on the client side, 80% in the database. Java took 11 minutes, the C takes almost 7 minutes. If we compare that with the PL-SQL constellation, so the time spent in the database of the C program, there is still a significant difference. It went down from 2x to 1.6x. Still a significant difference. So I'm going to continue working on explaining why the Java solution is so much more slow.
So,
Question?
it's more of a comment than a question.
Oh.
I think it's really important that you compare the area. I think that a lot of people might look at utilization at 2.0 minutes in and go, my database is busier using PL-SQL than it is using Java. So therefore, the Java is pretty less motivated. It's really, really, really important to understand that the area is what matters, not just the height.
Yeah, it's really important that you look at the area and not the height. Yeah, but I think I'm doing that, not? Yeah, okay, yeah. I have the same batch process using much less database time. And I've moved the business logic in the database.
I'd also make a comment that you're eliminating the network. The client's on the same machine, so comparing full comparison of machine utilization, you've got 204 CPU seconds on the machine for the PL-SQL there, but the full 6.5 minutes, you're using 100% of the machine with the C model.
Yeah, I'm using 100% not of the machine, of a single core on the machine. And this is a multi-core machine, obviously.
But, I mean, you're still using that much of the machine, so the database could be using that for something else. The client is doing that 20% still.
Yeah, maybe you and Carrie need to talk after this. Because you sort of like say the exact same thing from a totally different angle.
Well, my point is, you're paying for 20% of an enterprise edition license potentially that you can't use it all because the client is consuming.
Mm-hmm.
It's worse
Yeah,
than just
yeah.
the break
Well,
that you've got there.
This is a lab environment. The machine is dedicated for this batch process. Obviously, in the real world, there will be lots of other stuff going on, and the other 20% will be used by the other stuff.
Yeah, but if you've got a client that's using it, it's something right under the business that you can put bills on.
Yeah.
You're paying for the database license, you can't use it all, it's the client.
So we have a couple of questions now. Why is PL/SQL so much faster in row-by-row processing? Because we're still in this row-by-row processing context. Why is COCI outperforming Java JDBC? I'm going to spend just one slide on that. I'm going to spend most of the rest of the presentation on the first question, and then conclude with what does all this mean? So why is PL/SQL so much faster? I call this the living room analogy. PL/SQL is already in the living room, and I'm going to explain this in the next few slides, which is where the SQL engine resides. All other technologies, all other no PL/SQL solutions, they have to come in via the front door, sort of like wipe the feet, walk through the hallway, and only then enter the living room where the SQL engine lives. There's code path involved for these other technologies, which is not there for PL/SQL. A simple visualization of this, we have the PL/SQL engine inside Oracle, talking straight to what's called OPI, the Oracle Programming Interface inside the kernel of the Oracle database. Other technologies that submit to SQL, well, not in this case because I was running on the same server, but normally they would come in via the network interface. The OS gets a network interrupt, the interrupt gets serviced, it gets handed to the dedicated server that's actually listening on the socket where the message came in. And then inside the kernel, you have to traverse quite a few layers. Protocol adapter, TNS, there's always SQLnet, some 2-task code, and then finally you're at the OPI door and can submit your SQL statements to the SQL engine. So there's more code path involved, and I'm going to visualize that via flame graphs. Who is familiar with flame graphs? Who's absolutely, so the majority has never seen them, so I'm going to spend a few minutes explaining what is a flame graph. In Linux we have a process profiler called perf. And with perf I can attach to a process, and I'm using perf to attach to the dedicated server that is servicing the SQL statements. And perf can, let's say 100 times per second, or maybe many more times per second, dump the code stack that the process to which it has attached to is currently in. So using perf, I get a huge file with all code stacks, time-wise, that this process was in. A nice way to visualize then all the code stack and the time spent in which code stack is a flame graph. There's this guy called, what's his name, Brendan Gregg, who wrote a couple of Perl scripts that has as its input the file that was written by perf, and that creates a scalable vector graph file which you can look at in your browser. So it creates an SVG file that you can look at in your browser. And let me show you one. So here I have a flame graph. And what you see is inside a flame graph, remember, we have many different code stacks. So this function has called that function, has called that function, has called that function, and that's where we're currently in. And the next 100 seconds, we're in a different function. So inside a flame graph, all these code stacks get ordered from the bottom up, which enables you to look at how much time is, for instance, spent in OPI exe. Well, from here, it says almost 61% of the time, so the width of the flame graph represents sort of like the CPU time spent, because perf will only catch a code stack when the process is not in a wait, so the width of the flame graph is a representation of the CPU time spent. And inside the flame graph you can nicely see exactly where is time spent. So inside OPEXE we see a delete, we see an insert, so 21% spent doing inserts, and then all these other strange internal C functions that are inside the kernel. In a flame graph, you can click on one of those, it will then zoom in on it. So now I've clicked on KSU KOP and it shows me the flame on top of that, how much time is spent inside KSOPP. So this is sort of like the self time in KSOPP. And all the other times KSOPP had called a different function, either that one, or either that one. Yeah, so in a flame graph you can sort of get a really nice breakdown of where in the code that process was during the time that your perf profiler was attached to this process. So here's the flame graph of the PL/SQL run. And what it shows is that, yeah, PL/SQL underscore run. It shows this that we're inside the PL/SQL engine the whole time, because that one goes from left to right. We're inside PL/SQL the whole time. And there's a bunch of recursive calls going on, because I can look up these functions since I work inside Oracle, so these are recursive calls. That little flame on the left there. Then the EFN0, that's execute and fetch of queries. So execute the query and fetch the rows that the query might have identified. There's deletes going on, del exe. There's inserts going on, and we can actually see the proportion of the time that this all takes. Then there's lots of various other stuff going on, state initialization, mapping from cursors, etc. And then here, that's the PL/SQL code flame. That's the actual procedural lines inside my stored procedure being executed. Yeah, so we can get a nice breakdown of where is time spent. Now let's take a look at the Java flame graph. Not the JVM process, but the dedicated server that was servicing the SQL statements that were submitted from JVM. Looks a bit different. We have these huge two spikes on the left. Can you read it? NB receive and NBS send over here. Receive, send. That's just shipping data in and out of the database. Getting the SQL statement into the kernel, or the insert into as values, all the values into the kernel before we can start doing stuff. There's a little subflame there where we have to do what's called converting the on-wire representation of data values into internal representation of these data values. And then we have the stuff that we saw with PL/SQL also. The deletes, the inserts, the query executes and fetches ordered a little bit differently, and all the other stuff that we saw in the other one. Yeah? But we have roughly 30% of the time additional workload here, because we're entering the kernel every time and we're exiting the kernel every time, 5 million times, for 5 million SQL statements that get submitted. But 30% is not 2, right? We're still missing a lot. We saw it took twice as much, not 30% more. So let's stretch these two flame graphs into proportion. So on top I have the PL/SQL dedicated server, which took 204 CPU seconds, and I've stretched the Java flame graph wider so that it proportionally represents the 437 CPU seconds that it took in the dedicated server. So what's happening in the PL/SQL, in the thick database solution? We're inside PL/SQL and we're executing PL/SQL text. And at some point we might execute a delete statement. And some other point we execute an insert statement. But we're in the top of the flame all the time. Yeah, we go back to some PL/SQL code lines, and to the left and we do a SQL statement, we go to some PL/SQL code lines. We're in the top of the flame all the time. Now in the no PL/SQL world, we're outside. Some business logic procedural code is being executed outside. And it submits a SQL statement. We have to enter the kernel code. So we're receiving data. Maybe even converting some data values that are inside the SQL statement. And then we execute, let's take a delete statement at the same time here. And then we're going out again. We have to convert back to on-wire format. And make sure that this all gets sent back to the Java virtual machine. So not only is there a 30% width that gets executed more, but there's also depth in the code stack that gets executed more. And I'm visualizing these black arrows as if they go around the flame, but that's not true. Right? They just go up and down these different code stacks that are in delete and inside the receive and inside the send, etc. But the hot code is what I just told you. In a PL/SQL flame, it's just the top part. In the no PL/SQL, it's everything for every one of those 5 million times a SQL statement gets executed. Yeah? So we're also spending way more time in these layers over here, apart from the fact that we're spending time here. This is little time. This is supposed to be little time. We make it as efficient as possible, but still it's time. We have instructions to be executed in these layers. Now let's dig a little bit deeper. I was looking at the delete, and remember, I've stretched these two flame graphs into proportion. But if you actually look at the width, for instance, of a delete, it's exactly the same code, but it's wider in the no PL/SQL solution. So there's something else going on here also. Let's dig a little bit deeper. Why are we spending a little bit more time in each function in the no PL/SQL version versus the thick database version? Well, we can use another way. We can use perf and attach it to the dedicated server process to get some CPU statistics. What's going on inside the core that is servicing, that is executing the instructions of the database kernel. And we can get insight in things like how many instructions have actually been executed and how many clock cycles did it take to execute these instructions. And there's a very important metric called, on the right top there, instructions per cycle. How many instructions, on average, get serviced per clock cycle of the CPU core. Other things that we will look at are cache references and cache misses. Modern cores have what's called level 1, level 2, level 3 caches. And when an instruction requires some data and it's in the cache, that's a good thing. If it's in a further cache, it's still good, but it takes more cycles to get it. But if it's on memory and it's not in a cache, then the instruction will cause a memory access and bring in this data value into the cache. And this is counted as CPU against your process. We've ran this many, many times, and what we consistently see, and this is also true for the COCI run, which I'm not showing here, what we consistently see is that the no PL/SQL run retires less instructions per cycle than does the PL/SQL run. Yeah, we see almost 0.7 instructions per cycle retired in the PL/SQL run, but 0.55, and that's a significant percentage difference, which also gets added to the 30%, to the depth, and to the whole thing, and now we're nearing this factor 2. And these, so no, let me make one thing clear first. So we can without doubt see that the no PL/SQL run is actually executing more instructions. 50% more instructions, requiring 90% more CPU, and this brings us to the factor 2 now almost. And this is all caused by more branch misses in the no PL/SQL constellation and more data cache misses in the no PL/SQL constellation. Why is this? For instance, the data cache misses. Why would that be the case? More hot, cold? Well, we were entering the kernel every time, and we're going away every time. And when another SQL statement comes in, our dedicated server has to wake up again, hopefully on the same core. I think it will be on the same core, but it might not be on the same core. And the cache values, the caches may contain lots of other stuff of a totally different process that was just on the core while we were in the JVM. Yeah? Of course, there's always a little bit going on a machine, although I was having this machine to myself. Consistently worse branch and cache misses, which give rise to this considerable worse instructions per cycle. Yeah, so it's what I just said. The OS has to wake up, schedule the dedicated server to start running. Once it runs, hopefully on the same core, or all the code and data caches are likely full with stuff from another process. In the PL SQL run, this is not true, because I'm running all the time. And the only time when I get off the core is when the OS decides to schedule me off and put something else on. So your point is you have much more code traversal every time, so it's more likely that you are flushing your own code cache also. Yes, true. Yeah. I didn't spend any deeper thoughts or measuring on this. It's just an observation that I see a much worse IPC in the no-PL SQL. Yeah, so we have these three things: shipping data in and out, having a more deep code stack for every SQL statement, and the worse IPC, and added up, these give this factor 2 in terms of additional database load when you move the business logic out of the database. Ergo, the SQL statements out of the database. So I also wanted to say one little thing about why was COCI outperforming Java, because we only saw a factor 1.6 for the Java solution, in terms for the C solution. Well, the flame graph has a very similar shape. Again, at the left we see these huge two spikes for receiving and sending data, and we see the exact same things going on, like deletes, inserts, fetches, and some recursive stuff, etc. But if you zoom in, there are actually differences. It looks like OCI is privileged in the sense that when it enters, the database knows it's an OCI client, and there are various little things inside the kernel that get traversed a little bit differently. One of the things, actually two things that I noticed was there's an extra layer here which isn't in the COCI on top of OP ODR. It goes straight to OP exit. Here there's the KPO AL8 before it goes to OP exit. And there's actually some self-time there. And there are other differences. For instance, the little hop for translating from on-wire to in-memory format and back and forth, it's not there in the OCI. Apparently, some translation, some conversion takes place on the client already for this case. Of course, OCI was there for the first. OCI was the first to be there, so it's probably, it has some privileged ways of connecting and getting its work done in the kernel. So far I've been talking about the database server and explaining why it takes twice the amount of CPU when you move your business logic out of the database. But let's spend a minute or two looking at the client, because that's very interesting also. How much CPU is spent by the client, or is spent by the business logic tier? In Java JDBC, we saw 11 minutes times 33%, that's 271 CPU seconds inside the JVM. In PL/SQL, we can get this straight from an AWR. We look at the time model and there's PL/SQL elapsed time, and it's at 20 CPU seconds. COCI, 82, a lot faster than Java. So executing business logic in terms, if you look at PL/SQL versus very thin Java, there's a factor 10 difference. Can you imagine what the difference will be if you use a hugely layered approach inside Java? I know the figures, but they're not in this presentation. It's much more, much more.